Good morning, ladies and gentlemen. Welcome to this pair distinguished lectures. My name is Qingyan, the director of the PolyU Academy for Interdisciplinary Research. So today, we are very lucky to have Professor Deborah Chung from the University of Buffalo, SUNY University of Buffalo, to give lecture. So before that, I would like to ask Professor Mai to give the introduction to the speaker. Professor Mai, please.
All right, thanks very much, Professor Chen. Welcome you all to this lecture. So it is certainly my very great pleasure to introduce our distinguished speaker today. I actually knew Deborah for many, many years, but just to be sure, I just wrote down something here so that I can remind myself what I have to say. Professor Chung is a fellow of the American Academy of Arts and Sciences and is SUNY Distinguished Professor at the University of Buffalo. Professor Chung is a pioneer, an international leader in the field of multifunctional structural materials. In fact, the first time I know about her work, which is her best-known work, is Smart Concrete, in which she placed some short carbon fibers within the concrete, and that if there are any cracks or whatever deformation occurred, then you could detect it, and the volume electrical resistivity. And this is really one of her most distinguished work. Smart Concrete actually provides a springboard for her to achieve many other further research in multifunctional materials and their applications. And there are many of these. I think she will explain this in the lecture. Professor Chung always emphasizes on interdisciplinary research. And this is actually the hallmark of all her work. And in her book series, I think she might mention this later on, The Road to Scientific Success. And Professor Chung mentioned that the courage and willingness to cross disciplinary boundaries and jump out of your own comfort zone into the more challenging world is a significant that provides a chance to make significant impact in research. And that is exactly what she did in the last many years. Her research impact and excellence are demonstrated by more than 600 Vevry journal papers and 10 books she has written, as well as many honors she has received. I think most notably would be on the Stanford League table. She's ranked 14th, I think now maybe 13th in the world in overall citations in the subject of material science. And she is perhaps a role model for many of our female colleagues and students, the first among all women scientists in material science. So that is a very, very rare honor. And now, I mentioned I've known Professor Chung since the early 1990s, when I was actually working in the other institution, the Hong Kong USD, HKUSD. And in fact, her journey as a material scientist is really fascinating and very inspiring as well. I think Deborah would not mind if I say this. she actually began her education at Yinghua Girls' School, right? And then she spent 1 year lower six at King's College. King's College is just located below Hong Kong University. And so everybody would think that she would go to Hong Kong U. But also remember, in those early years, King's College just started to register or enroll women students. So you must be one of the first cohorts of female students at King's. And unfortunately, she did not stay on to go to Hong Kong U, but she decided, I think she was inspired by, the man landing on the moon in '69, and she thought that she would do better in the US. So she went to the very famous liberal college called Wesley. And then from there, she transferred to Caltech. So in 1973, she received her engineering degrees, both bachelor's and master's degree from Caltech. And she was one of the 4 first women who got their first, that means their bachelor's degree from Caltech at that time. So this is something I know Deborah always treasure. And she later obtained her PhD on graphite intercalated compounds in 1977, and at MIT, advised by Professor Mildred Dresselhorst, and regarded commonly as the queen of carbon science and also nanotechnology as well. And their pioneering works certainly attracted a lot of citations, and also opened up subsequent avenues of new research for Deborah because of the word carbon. Anyway, today, Professor Chung will enlighten us on the scientific wonders of carbon fibers, their multifunctionality. So, ladies and gentlemen, let's give a warm welcome to Professor Deborah Chung.
Thank you so much, Professor Mai, my very old friend. And it's wonderful to be here because I almost grew up here because my father worked here and I was just a kid at that time. Well, I'm going to talk about carbon fiber, particularly the continuous form of carbon fiber, because of its high modulus, high strength, and low density. It's very important for high performance, lightweight structures. The carbon fiber reinforced polymer refers to polymer matrix composites reinforced by continuous carbon fiber, and that's abbreviated CFRP, and that's my focus here. And that CFRP is utilized for aircraft, even cars, and bicycles, and turbine blades, and robot arm, a golf club, tennis rackets, and even for retrofitting damaged concrete structures. These properties of carbon fibers have received attention: mechanical, electrical, thermal, and chemical properties. But I'm going to emphasize in this talk electrical properties because those properties enable multifunctionality in structural materials. That means the material serves structural as well as non-structural functions. So no device involved, low cost, high durability, and no mechanical property loss. Also design simplification and large functional volume. So structural self-sensing is the most basic non-structural function, meaning that a structural material sensing itself without any sensor incorporation. And the science of that is based on the structural property relationships, with the properties being the electrical properties. And that means the structural material, as represented by this cube, it gives an electrical output, that is the electrical behavior changes in response to the loading or the damage. So no sensor, the structural material itself is the sensor. Now, aircraft can get damaged, say by bird strike, and aircraft tends to be made by in the form of composite laminates, which consists of a number of laminae or plies that are glued together. The interface between the plies is the weak link. This is a microscope view of two plies or two laminae with the interlaminar interface in between. And that interface is the weak link. And I developed an electrical method to zoom in electrically at this interface by measuring the contact electrical resistance. And it turns out that there's always a degree of fiber-fiber contact across this interface. And so the resistance is never infinity, and it's very sensitive to delamination and other factors. This is an example of that. The contact resistance of the interlaminar interface decreasing irreversibly upon impact at progressively increasing impact energy in millijoules. Okay? Every time one impacts, the contact resistance decreases irreversibly. And even at a tiny impact energy of 0.8 millijoules, we can detect it. So sensitive. And this irreversible decrease in the contact resistivity of the interface upon impact is due to the irreversible increase in the fiber-fiber contact across the interlaminar interface. So I'm going to talk systematically about the electrical properties of CFRP, conductivity, permittivity, and inductance. The conductivity is the first. It's been around for a long time. People have discussed about the conductivity of carbon fibers for decades. The applications that exploit the conductivity include lightning protection, icing, de-icing, and anti-icing by resistance heating. Also, electromagnetic interference shielding to protect electronic devices. Also, battery electrodes and supercapacitor electrodes, those require conductivity. In addition, structural self-sensing based on resistance measurement. But the catch is the material must be conductive, right? If it's not conductive, it's an open circuit and no story to tell. Here's just one of the examples of structural self-sensing by resistance measurement. This is under flexion. Okay, and one side is feeling tension, the other side is feeling compression. And we can sense both sides separately and simultaneously by measuring the surface resistance on either side. For each side, we apply 4 electrical contacts, the outer 2 for sending in current, the inner 2 for measuring the voltage. And so the top surface resistance and the bottom surface resistance get measured. And this is the compression side's surface resistance, shown in thick line. And every time one flexes it, that compressive surface resistance decreases quite reversibly. In the tension side, it's just the opposite. Okay? The reason is that for the tension side, the resistance increases due to the fiber waviness decrease. That is, you're kind of stretching it. So the fibers become less wavy, and so less touching between the fibers along the vertical direction. And so the current penetration decreases, and thereby the resistance increases. And the opposite applies for the compressive surface resistance. Since conductivity has been exploited for a long time, I'm going to push on to permittivity and then inductance, which are the 2 newer topics. Okay, permittivity. Polarization gives an electric dipole, and that means the separation of the positive and negative charge centers. And the permittivity really means the polarizability, how easy it is for an electric field to suck the charges, negative charges one way and positive charges the other way, and so you have an electric dipole induced. And one can do this sucking using a DC electric field, and the electric dipole resulting from this polarization opposes conduction. Okay, the polarity opposes the polarity needed for conduction. As a result, as polarization occurs under this DC current, the apparent resistance increases. Okay, the true resistance doesn't change. The apparent resistance increases. But if you suddenly reverse the polarity, the polarization doesn't reverse instantaneously. So you get to a situation here where the polarization actually aids conduction. As a result, the apparent resistance decreases abruptly upon polarity reversal from R1 to R2. Okay? Applications exploiting the permittivity include all conduction-based applications because the polarization hinders conduction. Also, the following specific applications. And the capacitors are needed in electronic circuits. Okay? And a capacitor involves two electrically conductive plates that are separated by a certain distance, and polarization of the material between the two plates results in the charge Q, okay, plus Q on one side and minus Q on the other side. And the capacitance C is defined as Q divided by V, where V is the voltage. And one can make a capacitor out of a structural material. In fact, I was the first to do that about 20 years ago. Very interesting functionality of structural material. Also, batteries and supercapacitors need permittivity materials, particularly for the electrolyte. Okay? Another application is structural self-sensing by capacitance measurement. And the nice thing about this form of structural self-sensing is that the material does not need to be conductive. Okay? So the applicability is even wider than the resistance-based self-sensing. Now, the carbon fiber that I'm going to talk about is conventional, pan-based, a 7 microns diameter, straight, with this typical resistivity, which is the same for single fiber and tow. By a tow, I mean a bundle, and in this case, 12,000 fibers in a tow. And the fibers in a tow are simply resistors in parallel. And that's indicated by the fact that the resistivity is the same for a single fiber and for a tow. Okay. Now, poling means the application of high voltage or high electric field to cause that sucking, that polarization. And here, each arrow indicates an electric dipole, and upon poling, they line up. But no poling is needed in any of the stuff that I'm going to talk about. And poling is not feasible for large structures anyway, due to the required huge voltage. So we measured the relative permittivity, AC, for single carbon fiber is 8 times 10 to the 7. For the tow, it's lower by 4 orders of magnitude, 1.2 times 10 to the 4. So 4 orders higher for single fiber than the tow. And that is because the tow amounts to 12,000 resistors in parallel, and hence the resistance is 4 orders higher for the single fiber and the tow. And a high resistance helps the establishing of a high electric field needed for that sucking. Now, if that tow were 12,000 capacitors in parallel, then the tow permittivity would have been 7 times 10 to the 3, which is less than the measured value. Hence, the tow is not exactly 12,000 capacitors in parallel, and that's because of the fiber-fiber contacts in the tow. And this is what I mean by the fiber-fiber contacts enabled by the fiber waviness. This is colossal permittivity. The permittivity as high as 10 to the 8th is higher than that of non-conductors by orders of magnitude. And this is due to the low electric field needed to cause the carriers to move in a conductor. And this colossal permittivity actually was predicted theoretically for conductors in general by Johnscher back in 1999. Now, the conventional polarizable materials are all insulators, ceramics and polymers. But now I'm talking about polarizable conductors, and they exhibit colossal permittivity. Now, one can do rolling, particularly if it's a metal. The carbon, you can't do rolling, but metals, you can do rolling, and the microstructure is refined by the rolling. So we want to look at the effect of rolling on the permittivity of metals, copper and steel, and we find that the permittivity is significantly increased by the rolling, and that is by the microstructural refinement. And so the microstructure, the refining of that is very important for enhancing the permittivity. Now, the polarization of a conductor requires a degree of interaction between the mobile electrons, which we call carriers, and the atoms. If there were no such interaction, the electrons would just loop around the circuit, just loop around. No polarization happens. But if there's some interaction between the carriers and the atoms, then you get polarization, plus minus here. So the polarization in a conductor is due to that interaction. And it involves a very small fraction of the mobile electrons with the atoms. And the interaction is mainly occurring at the microstructural heterogeneities, such as the grain boundaries. Thus, rolling increases the permittivity. And polarization involves the engagement of this interaction, whereas depolarization under reverse polarity involves the disengagement of this interaction. To look at the effect of grain boundaries, we also looked at graphites of various grain sizes. And we find that as you decrease the grain size, the relative permittivity increases greatly. And if we plot the relative permittivity versus 1 over grain size, it's more or less linear, indicating that the carrier-atom interaction occurs mainly at the grain boundaries. That inherent polarization, that is poling not needed, also leads to inherent AC capacitance. So the capacitance is inherent, and you can kill it by short-circuiting the thing. And after that, if you open circuit it, it will go back. This is self-charge, a new term, self-charge. Okay, I already explained this DC polarization, and this schematic picture here it shows what I call polarization, depolarization symmetry. You see this R1, R2 is symmetrical, okay? But in reality, for materials, very often it's not symmetrical. That is shown here. You see the curves get more and more asymmetric as the DC current increases. Also, the highest point, that plateau, it becomes higher and higher, meaning more polarization as you have higher current. Okay. So this is polarization, depolarization, asymmetry, which is natural there. Okay. And for carbon fibers, both uncoated and nickel-coated carbon fiber, here is just as is, you see, very asymmetrical. But if you do short-circuiting so as to depolarize it just prior to the electrical measurement, see, it's symmetrical for both the uncoated and nickel-coated carbon fiber. And also note that the curve is higher up for the nickel coating than without. So the nickel coating enhances the polarization due to the increased carrier concentration. Nickel is a metal, carbon is not. The polarization, depolarization asymmetry is due to the difference in the rate of the carrier-atom interaction engagement and the rate of the carrier-atom interaction disengagement. And so most importantly, you see that naturally it's asymmetric. I already mentioned that rolling can cause the microstructure to be refined. And so we looked at metal, copper, and this asymmetry gets more if you cold rolling, 37% versus 0%. And if you anneal it afterward, you just kill that thing. And so it becomes very low in polarization. That is, the curve is kind of low, and also it becomes symmetric. So cold work enhances this asymmetry, and annealing reduces it. And so the microstructure strongly affects the behavior. Electret refers to a permanent electric dipole. Okay? And conventional electrets are all insulators. And inherent electret is what I want to talk about. That is, you don't need to pole it. And it gives a small voltage, not a big one, and the voltage changes sign upon polarity reversal, as you would expect. And so this voltage is inherent, but then you can kill it by short-circuiting it. It would discharge. And after that, if you open circuit it, it will come back. This is self-charge. This is the result for a carbon fiber tow, as showing 3 cycles of discharge and charge. So again, you know, short-circuited discharge would kill the voltage, and then after that, open-circuited charge restores that voltage. The electric field inside the electret gets bigger as you decrease the grain size. Another indication of the interaction between the electrons and the atoms, particularly at the grain boundaries. Now, if you increase the amount of prior code work, the inherent electric field increases. And also that degree of asymmetry, what I call polarization, depolarization asymmetry, also increases. So there's correlation between that asymmetry and the presence of the inherent electric field. And both are enhanced by prior code work. Very importantly, the positive end of the voltage is where the rolling starts. This means the electrons move with the atoms during the rolling. Another clear indication of the interaction between the electrons and the atoms. So I see twofold mechanisms for the electret formation, electrical and mechanical. The electrical side is represented by that asymmetry. The mechanical side involves the directional deformation, as in rolling. Now, I mentioned about the capacitance, C equaling Q over V. And that is the usual capacitance, which we call permittivity-based capacitance. That's conventional. And as also known for conventional capacitor discharge, you know, it was just discharge and charge back in an exponential fashion. That's well known for conventional capacitors. This is permittivity-based capacitor. And here's C equaling Q over V, with V driving Q. But I'm introduced a new scientific quantity. That's the electret-based capacitance, which I define as C prime equaling Q prime divided by V prime, where Q prime is the electric charge as determined by discharge testing. That is current versus time. You integrate the area under the curve. That gives you the charge. And that is the Q prime, the electric charge. And V prime is the electric voltage. And so C prime is the electric base capacitance, and with Q prime driving V prime. And it turns out that the C prime is higher than C by, say, 9 orders of magnitude. It's just a different quantity. You might wonder, well, what's so great about this quantity? Just dreamed up? Well, it matches experimental results. The usual capacitance, the discharge time constant is RC, right? RC time constant. The discharge energy is half CV squared. In this case, the discharge time constant is RC prime. The discharge energy is half C prime V prime square. And this has been experimentally shown for a variety of metals and carbons. This means the electret discharge charge simply boils down to the electret base capacitance discharge and charge. Applications of electrodes include electrode filter. The COVID masks involve electrode filter. And one can also envision building for cleaning the environment with the facade involving electrode. Also, the battery electrodes and supercapacitor electrodes, they may be improved by having electrodes in the electrodes. Also, low power source. The power I'm talking about is very low, but there is a need for low power source. So permittivity behavior, I summarize: colossal permittivity. Capacitor electrode discharges upon short circuiting and charges back upon subsequent open circuiting, and this is self-charge. And the polarization is inherent. Holding is not needed. The inherent polarization, depolarization asymmetry can be removed by short circuiting. And the directional mechanical deformation strengthens the electrode behavior. The tailoring of the permittivity behavior of conductive materials is an emerging field of science. Also emerging is the field of structural permittivity, that is, structures providing permittivity-based functions. Now I move on to the third type of electrical properties, that is the inductance. A conventional inductor is in the form of a metal coil. And if you pass a current through the coil, you get a magnetic field along the axis of the coil. And the inductance L is related to the number of windings in the coil as well as the dimensions. Physically, the inductance is the tendency of an electrical conductor to oppose a change in the electric current flowing through it. So in red is the primary current, in green is the opposing induced current. What I'm interested in is not the coils. That's very old. What I'm interested in is uncoiled material, particularly uncoiled structural material serving as inductor. This is a really emerging field. The attraction is that without coiling, it's compact. And we can imagine structural inductor, that is a structural material performing inductor functions. That is a new functionality of structures. And this is the cross-section of a single carbon fiber, and you can see the crooked carbon layers, crooked, intertwined. And because of this microstructure, the uncoiled carbon fiber exhibits strong inductance due to the microstructure. And this is another view of the interlinking of the carbon layers in the carbon fiber. This is not coiling, but it's a bit like coiling. Okay? Applications exploiting the inductance include these. The inductor is an electronic circuit element. Okay? Power transformers need that. Electric generators need inductors. Motors need inductors. And almost 100% of electrical energy in the world is produced by generators, and the motors consume about 65% of electricity. Also, magnetic energy storage requires inductors. And also, structural self-sensing can be done by inductance measurement. So coils occupy space and are not mechanically good for structures, and we want it coilless. And we discovered that the coilless single carbon fiber exhibits very high inductance due to the microstructure. It's 2.4 millihenry per meter. It's higher than the value calculated based on the dimensions of the single fiber by a factor of 1100. The tow, as opposed to the single fiber, is much lower in the inductance, only 1.7 microhenry, not milli, but microhenry per meter. And that's simply due to the inductors in parallel inside the tow. And the fiber waviness, on the other hand, within the tow, helps to contribute to the inductance of the tow. The inductance, this is for single carbon fiber, can be essentially killed by short circuiting, and then restored by subsequent open circuiting. So this is a summary of the Oh, no, not summary yet. The single fiber inductance per unit length for the single fiber is 2.4 millihenry per meter compared to 1.7 microhenry per meter for the tow volume. So it's a difference by 3 orders. The ratio of the measured to calculated inductance is less than 1 for the tow, but it's up to 1100 for a single fiber. So the microstructure of a single fiber contributes to the inductance much more than the fiber-fiber contacts in a tow. Now, if the 12,000 fibers in the tow were inductors in parallel, the tow inductance would have been only 0.2 microhenry per meter, not the 1.7. So the tow is not exactly 12,000 inductors in parallel, and that's due to the fiber-fiber contacts that enhance the inductance. Now, I introduce another new scientific quantity. That is the surface inductance, as opposed to the volumetric inductance. What I talked all along was volumetric inductance. Surface inductance involves using a surface current injected from this from the same surface. Okay, so the partial current penetration, as opposed to the volumetric inductance, which involves current completely penetrating the whole cross section. And here are the results for the carbon fiber tow. The volumetric inductance is small, as I've already mentioned, 1.7 microhenry per meter, but the surface inductance is 4.2 millihenry per meter, and it's kind of close to the single fiber volumetric inductance of 2.4 millihenry per meter. And so the ratio of the surface inductance to the volumetric inductance is 10 to the 3, and that is due to a degree of inductors in parallel in the volume. Now, I want to move from carbon fiber to CFRP in terms of the inductance story. This is 2 cross-ply laminae, and the arrows indicate the current path tortuosity. And it's not coiling, but it's a bit like coiling. And so this tortuosity would contribute to the inductance. Sources of inductance in the fiber composites include not only the directional changes of the current path, but also the fiber-fiber contacts within the tow, also the tow-tow interface, and the interlaminar interface. So we measured the inductance of continuous carbon fiber woven reinforced polymer, CFRP, just one lamina, but woven like this, looking at the 0-degree direction horizontally and 45-degree direction horizontally. I want to, just in case you haven't heard of that, the Q factor is important for inductors. It is the ratio of an inductor's inductive reactance to its resistance. And the higher Q factor means lower loss and better suitability for use as a high-frequency inductor. And it's just given by this simple formula. So for the CFRP, these are the values of the inductance per unit length in Henry per meter. This is not millihenry. This is Henry per meter. Okay, and the surface inductance per unit length is 4.3 Henry per meter. Volumetric is much smaller. If you go 45 degrees, is even higher, 14 Henry per meter. The Q factor is also higher for the surface case than the volumetric case, and is higher for 45 degrees than 0 degrees. So the surface inductance is very interesting. But the Q factor is still not good enough. It's just 2.3. That's not good enough. So how can we increase the Q? Well, we need to decrease the resistance. And we have a simple way to decrease the resistance, and that's simply position an aluminum foil below or above the CFRP and measure the inductance of the CFRP aluminum combination. You can see that with the aluminum foil, the Q goes much higher, 9.15. Without the aluminum foil, it's 1.18. Okay, aluminum foil alone is so tiny. Okay, and so the foil greatly increases the volumetric Q, though the volumetric inductance is reduced due to aluminum foil. This is really new research. Okay, so far we have reached inductance of 14 Henry per meter by using the surface inductance, and we have so far reached Q of 9. Okay? A lot of room for improvement. This is really an emerging field. And how about increasing the number of laminae? I was talking about one layer, one lamina. How about increasing that? Well, if you increase the number of laminae, the inductance simply increases monotonically, higher at 45 degrees than 0 degree. This effect is interesting. If the laminae were inductors in parallel, the inductance should relate to 1 over n, n being the number of laminae. And 1 over n means that the inductance would decrease with increasing n. But this is just opposite to what we see. We see the inductance increases with increasing n. This means that the laminae are not inductors in parallel. The thickness increases with the number of laminae, obviously, and the thickness alone should decrease the inductance. Okay, but again, what you observe is the opposite. Thus, the inductance increase is attributed to the material structure, with the number of interlaminar interfaces increasing with the number of laminae, and the interface contributing to the inductance. And the interface contributes due to the fiber-fiber contacts across the interlaminar interface. There are other methods to increase the toe inductance. I don't have time to cover that. Twisting the fiber toe, tensile loading, that is piezo inductance. Also using nickel-coated carbon fiber as opposed to uncoated carbon fiber. All these help to increase the toe inductance. So this is a summary of the inductance behavior. Single carbon fiber exhibits volumetric inductance that is 1,100 times that of the dimension-based calculated value due to the microstructure. The volumetric inductance of a toe is much below that of a single fiber. The surface inductance, a new scientific quantity, is huge compared to the volumetric inductance, and the surface inductance of a toe is comparable to the volumetric inductance of a single fiber. The Q factor can be greatly increased by positioning aluminum foil above or below the CFRP due to the resistance decrease. The inductance is higher for 45 degrees than 0 degrees. The volumetric inductance of CFRP increases with the number of laminae. The tailoring of the inductance and Q factor of a coilless material is an emerging field of science. So here is my conclusions. Structural inductance and structural permittivity, two terms that I created, are provided by carbon fiber. And these are new functionalities for structures in general. And this work provides the initial science base for this emerging field. I'd like to dedicate this lecture to the memory of my late father, Leslie Wah-Leung CHUNG. I'm the little baby in this picture. In 1929, Hong Kong had a big event, which was the seafarers' strike. 海員罷工, okay, big deal. And because of that, my father's family went from being affluent to being very, very poor. My father attended Wah Yan College in Hong Kong for his secondary school education, but he skipped school a month at a time because of not being able to pay the monthly tuition. What a way to study. And then Battle of Hong Kong. Japan invaded Hong Kong in 1941. And my father was a member of the Hong Kong Volunteer Defense Corps, Yongguan, and he was actually wounded in action in Pak Sha Wan Fort near the Yumun. And this is that fort. And he was wounded with facial paralysis, with the mouth distorted, one eye not being able to close completely, and one ear not listening very well. And these problems were with him throughout his life. Actually, his being wounded was lucky because most of his comrades were killed by the Japanese army in St. Stephen's College in Stanley. And he received these British World War II medals. After the war, in 1949, he founded St. Mark's School, a Band 1 school in Hong Kong. And he started accountancy education in Hong Kong as head of the Department of Commerce and Management Studies in Hong Kong Technical College, which is the forerunner of Hong Kong Polytechnic University. This is a picture of my parents during a Christmas ball of Hong Kong Technical College. And my father was very proud of his accounting students because some of them become really prominent accountants in Hong Kong. Also, my father served as the president of Hong Kong Chinese Civil Servants Association. And as president, he fought for equal pay for equal work for women. And this is a picture with the Sir Hugh, who was the Hong Kong Colonial Secretary. IQ, intelligent quotient. EQ, emotional quotient. SQ, spiritual quotient. Emotional quotient means the ability to push ahead in spite of difficulties. Spiritual quotient means knowing what you're living for. What's the meaning of life? You know, all three Qs are important for success. And I really think that my father has exhibited all three Qs. You know, he has IQ, EQ, a lot of EQ, and also SQ. He really knew what he was living for. So I hope that his experience would enlighten you, and especially the young people here. Thank you.
Very much, Deborah. And I know you would talk about your father, so I did not say this. The other thing that Deborah did not mention is her mother. Her mother actually, she wrote a lot about her mother, which I read about. Her mother was a nurse, you know, and working with the Flying Tigers. I think it's in Chongqing, right?
In Kunming.
Oh, Kunming. Oh,
Yes.
not in Chongqing. Okay. So she came from a prominent family, very well educated, and that's why she is here. Anyway, maybe we'll talk about that later. The first is about the technical work you presented. Of course, the first one, I think many of us would know about with the resistivity of the carbon fiber. And then from the permissivity as well as the inductance, something certainly newer, which you are doing now. So maybe I'll open this for the floor if any one of you has any questions. I think there are many of us working in, yes, okay, Shen-Chi.
Professor Chung, thank you very much for your very, very interesting and inspiring talk. I actually had the pleasure to enjoy your talk when I was a PhD student back in UST many, many years back. But today, you presented something really, really new and inspiring, especially for the permittivity. So you mentioned about the using carbon fiber as a sort of a dielectric material with very high permittivity. So I'm just wondering, compared to those polymer-based dielectrics like polyimide, what would be the the advantage of carbon fiber because it's a conductive material, and how would really we could use it for the electric applications?
Great, great question. All those non-conductive dielectric materials, whether polymers or ceramics, they require poling. You know, inherently, it doesn't have the polarization. Poling is troublesome. Not only do you need a high electric field, after you have poled and take away the electric field, it can depole. And then you have to repole. And for a large structure, it's impossible to impose a high electric field anyway. So I think that is the most important difference. Actually, the permittivity of the carbon fiber as well as the other conductor materials is much higher, as I said, much higher than the values of the ceramics and polymers. And it's because it's a different mechanisms altogether. It involves charge carrier polarization. It's a different kind of polarization mechanism. But the electret, the voltage, is much higher for the non-conductive electrodes than the conductive electrodes. Okay, so there are plus and minuses.
Anyone? I think I saw Wang Tao. Yeah, I know you will ask questions because you work in this particular area.
Yeah, thank Professor Chung for such a wonderful talking. You talk about the polarization of carbon fiber. I just want to know what is the mechanism of this polarization. You know, for dielectrics, right, we normally have the ions, positive ion and negative ion, and then you can form dipole. And for a conductor, and what is the origin of this polarization? Is it due to the electronic polarization or the space charge polarization?
Yeah, it's the charge carrier polarization, and it's also space charge polarization because the carrier atom interaction occurs mainly at the heterogeneities, like grain boundaries, and that is really space charge polarization at the grain boundaries. But the inherent nature of the polarization stems from the difference in polarization rate and depolarization rate. As a result, you have this inherent asymmetry. And that is the electrical mechanism, I believe, for that inherent polarization. But I must say that this is just an emerging field. I don't, I haven't explained the physics completely. Yeah.
Have you also measured the dielectric loss? Any loss?
Oh yes, the dielectric loss is significant, obviously, because of the conductivity. Yes, so if you want to use it for electrical energy storage, the capacitor energy storage, then that loss would be no good. Okay. But if your application is not for electrical energy storage, that loss might not be so bad.
Okay, so for sensing is good.
Yes.
Okay,
Yeah, Professor Zhao.
Yes, thank you very much for your very nice presentation, Professor Chung. I think Professor Mai mentioned in the introduction, you have done some work on the smart concrete, detecting concrete cracks and all that. And recently we're working on floating structures using concrete. So the crack is very important. We don't have any cracks in the floating ponton, so obviously. So I was wondering, have you done in recent work on detecting cracks in concrete using carbon fiber and all that? What's the latest development in this area?
Actually, I've done that a long time ago already.
Yeah.
And it works really well.
Okay.
For instance, I could track the whole evolution of freeze-thaw cycling damage in real time by resistance measurement.
Okay.
It really works.
Okay. I'll maybe talk to you later. Yeah. More insight. Thank you.
Yeah, I suppose the one of the difficulties could be is too expensive to implement that concept, isn't it, in a large structure?
Oh,
Yeah.
carbon fiber is expensive compared to cement. However, actually, the sensing can occur even without the carbon fiber. Just that with the carbon fiber, it's a lot more sensing, more sensitive, and also more repeatable. It's more reversible. I mentioned about the freestyle cycling monitoring. I did it without carbon fiber, and it worked very well. Yeah.
Okay. Are there any other questions? Sorry, I can't. Where? Oh, yes, please.
Oh, thank you. Thank you. Thank you very much, Professor Zhong, and thank you very much for your nice talking. And I'm curious about what kind of polymers have you been used for the CFRP? And you know that still some polymers are not well compatible with the carbon fibers. Do you have any suggestion about for improve their interface compatibility for them? Thank you very much.
Yeah, I have used mostly good old epoxy. Yeah, for the CFRP, although also thermoplastic like nylon. And it's similar. For the thermoplastic, like nylon, is tougher, and so it's less prone for damage than the epoxy. But in terms of the sensing, it works either way.
Okay, thank you.
Anyone? Yes.
Sorry, one more question. So have you used these either dielectric permittivity or so kind of things, right, to sense the structural damage? When will the structure go from, say, elastic region, right, to plastic or even to the crack?
Yes, I have done that.
So,
yes.
what kind of signature can you observe?
Okay. There are two kind of mechanisms for that. One is that the permittivity is decreased by the damage. Okay, and so by measuring the permittivity decrease, you can tell the damage. That's one way. The other way is that the defects or cracks, whatever, would intersect the electric field lines between the two electrodes, thus decreasing the capacitance. So both mechanisms would allow capacitance-based self-sensing.
Actually, what I mean, when you add a load, right, you will always observe the decrease, the change in permittivity. What I want to know is how to determine the damage occurs. Are there any signature?
Oh, in general, if it's just elastic deformation, the electrical change would be reversible upon unloading. But if it's real damage, it's irreversible. So that's how I distinguish between the two.
Okay. Are there any other? Yes.
Okay. Thank you very much, Professor, for your very inspiring talk. As a cement and concrete guy, I noticed that recently people are using carbon cement. Basically, they mix the carbon with cement paste to make it like a supercapacitor. I mean, using concrete as a supercapacitor way. I was wondering, so can this carbon fiber you introduced here be used as something to incorporate with our concrete to make it to incorporate with some electrical properties like supercapacitor or supercapacitor or whatever?
Right, supercapacitors are a lot more challenging than just regular capacitors because you need the electrolyte, ionic conductor in between the two electrodes, and a concrete, a cement is an ionic, but it's a lousy electrolyte because it has electronic conductivity, not just ionic conductivity. So it cannot hold the charge because it's an electronic conductor as well as an ionic conductor. So it's challenging to use cement-based material as the electrolyte. which is needed for supercapacitors. Yeah.
Okay, and any other questions? Yes. Yes, please.
Hi, Professor Zheng. Thank you for your wonderful speech, and followed by the self-sensing question. I have a question is that I'm wondering how the carbon fiber is attached to the surface of the structure. Like if it is attached to the surface of the structure, and if the structure is like broken, will the carbon fiber be broken along with the surface of the structure? So if the carbon fiber breaks along with the surface of the structure, will the carbon fiber is be reusable or self-healing? Because in our common sense, if the surface of the structure it breaks, the capability of the sensing of the carbon fiber will break too. Thank you.
Yes, yes. What I emphasize is not coating a structural material by carbon fiber. I want the structural material itself to exhibit that self-sensing ability. Okay. If you do the coating, I agree with you. It can debond and lots of problems. But that's what I want to avoid, actually. And that's what I mean by self-sensing, you know.
Anyone else? No? All right, I think I don't want to ask any questions. Perhaps what we should do now is to close the Q&A session. So now the next is for the director of PAIR, Professor Chen, to present to you a souvenir.
We wanted to thank Professor Chen once more for the wonderful talk. And I also appreciate Professor Mai for chairing this session, Q&A session. It's very wonderful. And like to also thank all the audience here, especially those who ask questions, which really make this lecture very successful. So PAIR conducted the distinguished lectures once a month. So I hope that you will join our next lecture. Thank you very much. This lecture is adjourned.